Welcome AP Calculus students to day 6 of our free response question review, the AP Calculus exam. Today we're actually going to be looking at another AP Calculus exam since we finished in our previous lesson the 2019 free response question. So today we're going to be looking at a different year's administration. But let's get to our warm-up first, and then we'll get to our free response question of the day. So if y equals the integral from 3 to x of 1 over the quantity radical 3 plus 2t dt, then d squared y is equal to dx squared. All right. So hopefully, when you see this, you kind of think of the derivative, and even more specifically, you think about the second derivative, right? Normally, whenever we talk about the derivative or the first derivative, we look at dy over dx. But since this is d squared y over dx squared, this is the notation we look at to determine the second derivative. So this is basically just asking us to find the second derivative of this y equals equation. All right. Well, since this y equals equation is defined as an integral, recall that when we take the derivative of an integral, we're just left with the original expression. So dy dx is equal to 1 over the quantity radical 3 plus 2x. So that's all you're left with, right? The integral goes away because since the integral is the antiderivative, well, if you take the derivative of the antiderivative, that means you're just left with the original expression. Now, yes, it is true. Other things can happen depending on what are the interval values. But in this case, since our interval values are just a constant 3 and a variable x, that means our derivative just ends up being that original expression in terms of x. So nothing fishy going on. Now let's rewrite this. Before we take the derivative of this again to find the second derivative, let's rewrite this as 1 over the quantity 3 plus 2x to the 1/2 power, because remember, if you take the square root, it means you're taking it to the 1/2 power. And since it's in the denominator, we can rewrite it even further as 3 plus 2x to the negative 1/2 power. Because remember, when your exponent is negative, that means it's brought down to or you take the reciprocal, which in this case means bringing it down to the denominator. Now we can take the derivative of this, which will give us the second derivative. So we use the power rule, so negative 1/2. So negative 1/2, quantity 3 plus 2x, subtract 1 from the exponent, so negative 3/2, multiplied, chain rule people, chain rule, multiplied by the derivative of the inside, which is just 2, since the derivative of 3 plus 2x is just 2. Now it looks like this 2 and this 1/2 cancel out, so we're just left with that negative. So we end up with, if we turn that negative exponent into a positive, negative 1 over the quantity 3 plus 2x to the positive 3/2 power this time. 3/2 power, because since we took the reciprocal, or since we brought that expression down into the denominator, the exponent now turned positive, which looks like to be answer choice A. So answer choice A for this little warm-up of ours. Okay. Hopefully that went smoothly. So let's get to our free response question of the day. So this free response question will be a little bit similar to one we tried in the 2019 AP Calculus exam. So this is the 2015 AP Calculus exam. More specifically, this is the first free response question, so it does mean it is a calculator question. So I say that it's similar because it's one of those questions where they give you two rates, a rate that's going in and a rate that's going out, and then you have to answer a bunch of questions in terms of like the amount that's going in and so on and so forth. So the rate at which rainwater flows into a drain pipe is modeled by the function R, where measured in cubic feet per hour, and T is measured in hours, and T is between 0 and 8. Okay, so for this R of T, that's the rate at which rainwater flows into, and T is between 0 and 8. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by D of T, cubic feet per hour, for T less than greater than 0, less than 8. So D of T is water draining out, the rate at which water is draining out. So that's D of T. And T is still between 0 and 8. And then finally, there are 30 cubic feet of water at time T is equal to 0. So that's the initial amount of water. Initial amount of water in the pipe. So that's going to be significant eventually, once we start talking about the amount of water in the pipe. Okay, so part A. How many cubic feet of water flow into the pipe during the 8-hour time interval? So rainwater flow into the pipe. Well, hopefully you are underlining or circling some of the key words. The R of T function is the rate for water flowing into the pipe. So to find the amount of water that flows into the pipe, we're going to take the integral of R of T. So the integral of R of T gives us amount of water that has flowed into pipe. Okay, so since R of T is the rate at which water is flowing into the pipe, the integral of R of T is the amount of water that is flowing into the pipe. Okay, so we're told from 0 to 8. So from 0 to 8. So we take the integral from 0 to 8 of 20 sine t squared over 35 dt. So what is that equal to? So this is going to give us the amount of water that is flowing into the pipe during that 8-hour time interval. So if we use our little calculator here, bust out our calculator. So you'll see, I actually did this problem. This is actually the second time I've recorded this video. Unfortunately, the first time did not record. Pretty upset about that. So if you can see here, if we take the integral from 0 to 8 of that equation, 20 times the sine of t squared over 35, you would get 76.570. So 76.570. So 76.570 cubic feet. So that's our answer for A. That is our answer for A. All right, now B. Is the amount of water in the pipe increasing or decreasing? So an increasing or decreasing problem at time t equals 3. So what is increasing or decreasing? Well, this is not the first time we've done an increasing or decreasing problem. This time we were being asked if the amount of water is increasing or decreasing. So first, whenever looking at an increasing or decreasing problem, you have to look at that respective function's derivative. So that's your first step, is you want to find the derivative. You want to find derivative. Well, first thing we have to do is determine what function determines the amount of water in the pipe. So let's do that here. So amount of water, let's call that A of T. A of T. Well, if we revisit part A gave us the amount of water that was flowing into the pipe. Okay, so if you take the integral of R of T, that's the amount of water flowing into the pipe. Well, what if we take the integral of D of T? Well, D of T is the rate at which water is draining out. The rate at which water is draining out. So the integral of D of T would be the amount of water draining out. Okay, so we basically have to subtract these two amounts. We have to subtract the amount of water flowing in. So the integral of R of T. So the integral of R of T dt, and subtract that by the amount of water draining out. So the integral of D of T dt. Okay, a very simple example to think of is pretend during this 8-hour time interval, 5 cubic feet of water is flowing in. 5 cubic feet of water is flowing in. And during the same amount of time, 3 cubic feet of water is draining out. Well, if 5 cubic feet flows in, 3 cubic feet drains out, that means a total of 2 cubic feet is left over, right? 2 cubic feet is left over because we get that 5 minus 3. So that's a simple example to think of as to why the amount of water is determined by the difference of these two integrals. And we can rewrite this as the integral of r of t minus d of t dt. Rewrite it as just one integral. Now, once again, well, I highlighted up here that we want to find the derivative. So let's find the derivative of this. So a prime of t, well, if a of t is an integral, the derivative of the integral, just like we talked about in the bell ringer, would just be that original expression. So r of t minus d of t. So now we want to determine if this is increasing or decreasing. Now, recall, if the derivative is positive, means the function is increasing. If the derivative is negative, it means the function is decreasing. So all we care about this derivative, or this r of t minus d of t, is whether it's positive or negative. So that's all we care about. So determine if positive or negative. So that's what we're going to do. We're going to determine if it's positive or negative at 3. So a prime of 3 would mean we would have to do r of 3 minus d of 3. So r of 3 minus d of 3. So once again, I already did this up here. So there you go. So we plug in 3 for r of t, and then we subtract that by plugging in 3 for d of t. Now, the only thing I would watch out for this one is if you do notice that subtraction sign between them, and then I put the second equation in inside of a parentheses, because you do want to make sure you're subtracting by that entire expression and not just by that first 0.04 in front. So it looks like our answer is negative, so it's less than 0. So a prime of 3 is negative negative 0.314, which is less than 0. So we would say, since a prime of 3 is less than 0, the amount of water in the pipe is decreasing at t is equal to 3 hours. So just to put it as a complete sentence, it would be decreasing because it is less than 0. Okay. So that's part B. So once again, find the derivative, determine if it's positive or negative to determine if it's increasing or decreasing. All right, so now part C. Part C. So at what time t is between 0 and 8, is the amount of water in the pipe at a minimum? Justify your answer. So minimum, people. So this one is similar to increasing or decreasing. The first thing we want to do, and we're taking the minimum of the exact same thing, so the amount of water. So first step is still find derivative. So we still want to find the derivative. Okay. Now we already did that in part B, so our derivative was, where was it? Our derivative was r of t minus d of t. So now our second step is going to be different. Our second step now is to find critical numbers. So find critical numbers. So remember, a critical number is when the derivative is equal to 0. So we're going to find when the difference between these two functions is equal to 0. And once again, I did this already on here. So the way I did it is you want to graph this. So you want to graph, get it up here. So you want to graph, once again, r of t minus d of t, so 20 times sine x squared over 35 minus the quantity, so on and so forth. So you want to graph that. You want to plug that equation into your calculator and just graph it. And we get this purple graph. And then from there, since we only care about t values from 0 to 8, we don't care about this one over here. So we don't care about that one. So the only one we care about is this one. So you would just use your calculator on this little app. There's an analyze graph option and find the 0. So you're looking for that 0 option. and then you simply just say, so our 0 is in this region, and that's how you would get the 3.272. So there's only one t value that's equal to 0, so 3.272. All right, so t 3.272. Okay. So now we got to test this value in addition to the endpoints of the interval. Whenever you're given an interval and you're finding a max or a min, you have to test the endpoints of the interval. So we are going to be testing 0 and 8. So we're going to be testing that into a of t, into the original amount function. Okay? So we're going to be testing a of 0, a of 3.272, and then a of 8. So we're going to be testing those three t values. And we're going to make a slight tweak to that a of t equation that we had in part B. And the only reason why I say a slight tweak is because we have to take into account, so a of t is equal to that integral from 0 to t, r of t minus d of t dt. But now we're going to take into account something that we noticed in that when we were reading the original problem, which is the initial amount of water in the pipe. So at t is equal to 0, there was some water already in the pipe. There was 30 cubic feet. So we just have to add to this integral plus 30 to take that into account, right? We've got to take into account the fact that there was already 30 cubic feet of water in there. So a of 0 is just the integral from 0 to 0 dt plus 30. Well, since our integral is going from 0, starting at 0, stopping at 0, that means that's just equal to 0. So we get 0 plus 30, which is 30. Now we're doing the integral from 0 to 3.272 dt plus 30. And once again, I already did that here. So let's pull that up. Where are you? No, here we go. So the integral from 0 to 3.272 of that expression, remember r of t minus d of t, is equal to 27 plus 30, 27.965. So 27.965. So 27.965. And then a of 8, so the integral from 0 to 8 dt plus 30. Hopefully you can just copy and paste this one, even on a calculator, where you just have to change the 8. You might be able to do like the last equation or something like that, plus 30, and we get 48.544. So 48.544. So it looks like our max happens at 8. So we would say at t is equal to 8 hours, amount of water reaches a maximum. And that's it. So at t is equal to 8 hours, the amount of water reaches a maximum. So just to recap, we found the derivative, we found the critical numbers, and in addition to the critical numbers and the endpoints, right, those endpoints of the intervals, we plug those into the original function. So the original function was a of t equal that integral plus 30. You always do want to watch out for if you're given an initial amount, which in this case we were, so we had to put that plus 30 included in our calculations. And then finally D. The pipe can hold 50 cubic feet of water before overflowing. For t greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. So it looks like our equations don't change. Write, but do not solve an equation involving one or more integrals. So it's basically telling us right here that our answer involves integrals. That gives the time w when the pipe will begin to overflow. So as the problem states, when the amount of water reaches 50 cubic feet, it begins to overflow. Well, if you recall from part C, we have an equation for the amount of water. Part C told us that the equation for the amount of water is just the integral from 0 We're going to say W this time since it tells us find but do not solve an equation involving that gives the time W when this happens. So 0 to W of R of t minus D of t dt plus 30. So we just simply have to figure out, when does this integral plus 30 equal to 50? Because that's all it told us to do. Just write but do not solve the equation that would tell us the time W, and that's why I changed the interval value to a W. So if you were to solve for W, that would be the time you would take for it to reach 50. So that would be our answer. Not much. I mean, this is basically asking us to set the amount equation that we established in part C equal to 50, and that's it. Okay, well, that's part D. Hopefully this went smoothly. As usual, I do post the solution key to this. Hopefully you guys are, keeping up with these videos. Just trying to, like I said, I'm trying to expose you guys to as many of these free response questions as possible so that you guys are ready once that AP Calculus exam comes around. In terms of an assignment, you guys will be completing that Journey Through Calculus packet, so page 6 of that Journey Through Calculus packet. So make sure you complete that. It will be due by the time we meet next in class. As usual, it will be extra credit if you complete it. Just take a picture of it, send it over to me. Just email it to me. Otherwise, I hope you guys are staying healthy. I hope nobody's getting sick. I hope you guys are staying safe. At the same time, I hope nobody's losing their minds just staying home so much. I know I'm trying not to. But otherwise, I hope you guys enjoy the rest of your days, and I will see you later.